Hello everybody and welcome back to Prospect Charter School's Algebra 2 course. Today we're going to go over section 2.2, which is proportional reasoning. To go over this, we first have to know what a proportion is, and to do that we need to know what a ratio is. So a ratio is a comparison of two numbers by division. So a comparison of two numbers by division. And then a proportion. Can you guess what a proportion is? Yep, it's a comparison. It is a comparison of two ratios by an equal sign. So an example. An example of a ratio, poor ratio, man of infinite jest, most gracious fancy. Yeah, that's Shakespeare, by the way. Bill's pretty cool. You ought to read some of his work, especially his play Hamlet. All right, a ratio would be something like 3 to 5. So 3 over 5 would be a ratio. We have it's a good 3 to 5. We have 3 red cars for every 5 green cars. Something awesome like that. And then a proportion takes the ratio and compares it to another ratio. So a proportion would be 3 over 5 is equal to 9 over 15. 3 red cars for every 5 green cars is equal to 9 red cars for every 15 green cars. So it's the same thing. It's just that it's been scaled up. It's proportional to each other. So 3/5 is equal to 9/15. They're the same number. A ratio is basically, it's just a fraction. It's a comparison of two things by division. Now let's see some of these things in action. Let's say that we have a proportion where we don't know what one of the values is. Say that we're making dinner for a very big family, and we know that we have 2 cups of water for every 3 cups of rice. And the problem is that 3 cups of rice is not nearly enough for the family. We need at least 15 cups of rice. How many cups of water will we need? Well, to do this, I would put an x, or other variable, in the location of the thing that I don't know. And then I would solve, and I would solve through a method called cross-multiplying. Now, when you cross-multiply, this only works when you have an equal sign. It only works when you have an equal sign. No equal sign, no worky. Yes equal sign, yes work. So it only works when you have an equal sign. It only works when you have an equal sign. Don't do this to find a common denominator. This only works when you have an equal sign. All right. So when we have an equal sign, we can cross-multiply. We can take 15 times 2 and get 30. We can take 3 times x and get 3x, and then set them equal to each other. So that we would have 30, if I can draw a 3, we would have 30 is equal to 3x. And then we solve for x normally, which means that we would multiply both sides by 1/3, or divide by 3, whichever you prefer. And we would have x is equal to 10. So you cross-multiply, and then you put it together. Now this stuff is really easy. The problem is that you get these from word problems. And I know what you're thinking. Oh my god, word problems. Oh my god, oh my god, oh my god. Don't worry. Word problems are really easy. In fact, we'll go over a word problem together. So, an example. Let's say that we have a really awesome high school. We do have a really awesome high school. Let's pretend that we're at a different high school, and it's not quite as awesome, but it'll pretend to be as awesome. And at this pretend to be awesome high school, there are 434 students. So, 434 students. If 35% of them play sports, how many students play sports? Well, this is actually not only a proportion, but it's also a percentage. Percentages are proportions. They are the amount per 100. That's what a percent is. So if I'm looking at it, I'm given a percent. I'm given 35%. So I'm given 35 out of 100 students play sports. Well, how many total students are there? Well, there are 434 students. And how many of them play sports? So I put an X. So now we use our amazing math skills, and we can solve for X in this case. And we go, okay, 100 times X gives me 100X. And then on the other side, 434 times 35, pulling out my handy dandy calculator, 35 times 434 gives me 15,190. 15,190. All right. Now we take that 15,190 and divide it by 100, and we get 151.9. So, in other words, 152 students play sports at that not quite as awesome as Charter High School. Prospect Charter High School. All right. So percentages, they're really proportion in disguise. Go figure. All right. We've got that one down. Let's do one more. Let's do one when we have a unit conversion and some other things that are going on. For an example, let's say that we have a professional jogger. And this professional jogger wants to find out how far each stride is so that she can do some calculations. All right, so Rita, tell us how long a stride is. And she tells us, well, I don't know, but when I ran around a 400-meter track, it took me 328 strides. 328 strides for a 100-meter track. And she says, how many inches are in each stride? How many inches per stride? And of course, they're really nice, and they give us that 1 meter is equal to 39.37 inches. And we're like, okay, well, I got all the information, now what? Well, now we put them into proportions. For an example, if we wanted to find strides per meter, we would look at how many strides we have and put it per 1 meter. So how many strides do we have? Well, we have one ratio where we're given 328 strides, and we're given that it's a 100-meter track. So over here, for one stride, how many meters do we get? Using our handy-dandy calculator, we can actually calculate that. And we can say one stride is equal to, we go 328 divided by 100, and we get Can that be right? Yeah, 328 divided by 100 is 3.28. Oh, I see what I did wrong here. It's not a 100-meter track, it's a 400-meter track. I'm bad. Okay, there we go. It's a 400-meter track, so one stride would be 328 divided by 400, which gives us 41 over 50. So one stride per meter is equal to 41 over 50, which would give us 50 over 41 meters per stride, right? Because we do the cross multiply, and then we would cancel. All right, so I just reduced this one, strides per meter, to give us one stride is how much meters. So that'd be x down here, and then we would solve for x. That was really, really messy. I am really sorry about that. But if you look at it, if we cross multiply here, we get 50 is equal to 41x, and x is equal to 50 over 41. So we have 50 over 41 meters per every stride. Now we can use our next ratio to determine how long each stride is in inches. Now when we do unit conversions, I like to do something called a railroad track. I put up a little track like this, a horizontal line, and then on the top I put the units that I have. In this case, 50 over 41 meters. And then I would go along and I would use my unit conversions to get to my final location. And what I want is inches. Fortunately, I know that I have, according to this, 1 meter is 39.37 inches. So I would use that ratio. I would say 1 meter is the same thing as 39.37 inches. I would multiply across and then divide by the bottom after making sure that all of my extra dimensions cancel. So meters would cancel with meters. I'd be left with inches, which is what I want. And then I just do the arithmetic. 50 over 41 divided by 1 is, well, 50 over 41. And then we multiply that by 39.37, and we get 48.01 inches. So her stride is 48.01 inches. And I know what you guys are thinking. Mr. O'Neill, why did you leave it as a fraction? Why couldn't you just put it as a decimal? Well, as a decimal equivalent, it would be 1.22 meters per stride. And if we wanted to convert that into inches, we would have 1.22 meters. And using the railroad track system, we would still have that 39.37 inches per meter. And we get 1.22 times 39.37. And they should be the exact same number, right, if it was perfectly accurate. But we get 48.03 inches. It's off by 2/100ths of an inch. And normally that wouldn't be that big of a deal. But if you're looking at like a marathon, where you were looking at miles, 26 miles, that difference adds up really fast. And that can be the difference between like first place or 15th place. It's really huge when you go over long distances. So while decimals are nice, they are never as perfectly accurate as fractions. That's one of the reasons why I really love fractions. Fractions don't lie to you. They are as accurate as you can possibly be. All right. One more, and then we're done. We can do our practice, and then we can call it a day. For an example, let's say that we want to find out how tall a cliff is before we go rock climbing on it. Because Mr. O'Neill has a limited amount of stamina, he can only go for so far, and if it's too tall, he can't climb it. So we look at this cliff, and we're like, we don't know how tall this cliff is. But we do know that its shadow makes a length, and we measure that length, and it's 60 feet. So we know this cliff has a shadow length of 60 feet, but we don't know how tall it is. And then we have Mr. O'Neill standing over here. Oh, wait. Got to get an accurate picture of Mr. O'Neill. There we go. And for this one, we're going to call Mr. O'Neill exactly 5 feet tall. And he gives off a shadow that is 4 feet long. That, of course, creates another triangle. And these two triangles, because they are done exactly at the same time, are proportional. So because they're proportional, I can say that for a person who is 5 feet tall, they cast a 4-foot shadow. That has to be the same thing as an unknown tall item given a 60-foot shadow. And then we can cross multiply to find the exact height. 60 times 5 is 300. 4 times h is 4h. So obviously 4h is equal to 300. Which I definitely disagree with. 4H is an awesome agricultural program, while 300 is a crazy movie with weird stuff happening. So I'm going to have to say that these things are not the same thing, and I'm going to have to divide by 4. And when I divide by 4 to get h by itself, or multiply by 1/4, whichever you prefer, we get 75 is equal to h. So the cliff that Mr. O'Neill is considering climbing is 75 feet tall. This is an amazing method that can be used by forest rangers to determine how tall trees are without actually having to climb the tree. Isn't that awesome? The problem is when you get so dense of a forest that you can't tell where one shadow ends and the other begins, in which case you have other methods which you can learn from geometry in how to determine how tall an object is, just from a simple measurement. All right, that is all for today. Let's go ahead and start with our homework. Now, homework is going to be, or practice, is section 2.2, and we are going to be looking at page Who Cares, numbers, lots of them. Let's see, there are 71 problems. Yeah, we'll go 1 through 71 on. No? You don't want to do one? All right, fine. I'll be nice. Let's do 3 through 9 odd. And then 11, 13, 15, 17, 21, 23, 29, which is super easy, and then 33, and I think that might be all of them, 38. There are a lot of word problems involved with this, and I know you guys don't like word problems, but oh well, they're part of life. They are the transition between pure mathematics and the real world. And math is a tool. And if you have a tool that you can't use, what's the point of having the tool? It's kind of like that Monty Python thing where they had the machine that goes bing. It serves no purpose. So if it serves a purpose, then it's a good thing. Math, without being able to be used, serves no purpose. So word problems are what make math worth anything. So you're going to have to get used to them. You're going to have to get good at them. And considering that there's going to be a video out there about how to approach word problems, and a very effective one at that, you shouldn't have any problems with these. These are great practice for you. Anyway, I'm off my high horse, and I'm going to say good luck and have fun.